it's an almost fixed value, means almost DC value. Okay. So then that DC value will be compared with some repeating sequence. Okay, or you can say like that with triangular voltage. Okay, with that value will be compared with some triangular voltage. After comparing all those things, triangular voltage, directly we will get some PWM. Okay, and that PWM can be fed to the your solid state device. So you know that in power electronics applications, okay, in that converter applications, we are using what type of switches? Different switches we are using. Sometimes we are using different latching device, but that latching device is not used for our common applications. Okay, it's normal use for high power applications, but normally in our common applications, what kind of switch we are using? That is your MOSFET switch. Okay, so what is the benefit of the MOSFET switch? High switching frequency. Normally, we are working on the switch mode power supplies. Okay, that's very important applications of power electronics converter. So that switch mode power converters and that range of applications, that range of frequency also very high. If you are using MOSFET, so it can go up to 500 kilohertz. But problem is that it do not have MOSFET is a voltage control device and it can be go up to some range of voltage. So voltage range is not so much high. Okay. But what happened for the inverter applications? Okay, what we are doing, we do not require that amount of switching frequency. Okay, we require some more voltage boosting system, voltage and current carrying system more. So that's why we are using IGBT. Power BJT also be used, but power BJT is a current control device. Okay, so what we are doing for that IGBT, clubbing of BJT and the MOSFET, and we are designing one device. Not we are designing, that has been designed by some fabricator. Okay, that is your IGBT, clubbing both the devices. Okay, both the properties can be observed in IGBT. So it's don't have so many switching frequency, but it's a current control device. Also the losses will be negligible. Okay, so moderate device we have designed. Okay, that is called IGBT. So all those case, if you want to design the gate drivers, means control switch for that IGBT, it should not be same with your designing of the gate driver for the MOSFET. Okay, but okay, so some of the differences are there. For MOSFET, what we need to do, as it is voltage control device, so what kind of output we are getting from that? We are having some control, common gate driver circuit. Okay, if we pass through that one, through the resistance and that Smith trigger. Okay, so what happened? That current strain goes down. Okay, and we are easily implement those gate driver for our common applications of BJT, MOSFET. But what happens in case of BJT, as I am telling that current strength is less, so BJT is a current controlling device, so you have to use some more solid state device to amplify the current of that BJT. So what you need to use, you have to use the another two BJT. Okay, that is signal BJT, and we are talking about power BJT. Okay, both are different. Okay, so and your control circuit, that gate driver circuit, you can see the MOSFET biasing voltage is up to 15 volt. So voltage can be varied 0 to 15 volt, not beyond that. And whatever BJT we are using in the control circuit, okay, for driving that power BJT, okay, for driving the power BJT, that range also within 24 volt. Okay, so SL100, okay, like that. Different names are there. Okay, so we are using that amplifying the current. Okay, that's why what we need to do, we have to use maybe totem pole configuration or Darlington configurations and amplify the current of the BJT as well as 15 ampere, 15 volt pulse. Okay, and that can be able to drive the power BJT. Okay, and you will get some outcome from that BJT. So overall operations, overall circuit may be same, but some of the differences will be there at the terminal of just before the gate. Okay. Also sometimes we have to give some protections. Okay, protections means what? Okay, suppose huge voltage is coming. Okay, normally what we are doing for the MOSFET gate driver, so we should give the protection. So which terminal you will provide that gate pulse? One will be gate, another one will be source for the MOSFET. Okay, gate and source. So source will be grounded and you should give the what kind of ground? Gate driver ground. Okay, gate driver ground. Okay, if it is non-isolated type. Okay, there are two types of gate driver. One is called isolated gate driver, another one is called non-isolated gate driver. Okay, first we are starting with that non-isolated gate driver. Why isolated gate drivers are important? So, suppose you are designing a circuit for a drive circuit. Okay, where you are using IGCT. Okay, means high power applications. It will be more than it can be the range of 100 kilowatt. Okay, you are using IGCT circuit. Okay, what happened? Any faults is happened in your power circuit, and I am talking about that we are using that MOSFET. I'm just taking an example. Okay, so in case of IGCT, also that emitter terminal. I'm just talking about the MOSFET. Okay, and high range of applications, high power applications for the MOSFET. What we are using that common terminal that gate ground and directly we are connecting to the source and gate driver and another terminals means pulse terminal directly connected to the gate of that control switch. Okay, suppose any fault happened in the power circuit, then what happened? Okay, there is a, as both the cases ground is same, there is a high chances to flow the circulating current in between gate driver ground and power circuit ground. So if it is happened, then what happened? Can you imagine? It's as it's a MOSFET, we are considering it may be the 600 or 600 watt circuit, or maybe 100 watt circuit. And your gate driver, how much current rating? It will be in minimal for MOSFET. It's a minimal milliampere range current, and voltage is how much? We are talking about 15 volt. So if you multiply both of them, so 15 volt into some milliampere, 1 milliampere, whatever. So you can understand the rating, the power rating of that power control circuit. But MOSFET, but power circuit power rating is more. So automatically the control circuit will be damaged and burned out. That's why what we are doing when we are fetching, okay, when we are collecting the output voltage from our power circuit, we are using the transducers. Okay, what kinds of transducers normally we are using? Hall effect transducers. Okay, means we are isolating the circuit, control circuit with your power circuit when we are fetching the actual voltage, okay, through magnetic isolations. Hall effect and Hall effect sensors we are using. Okay, LEM is a company that's designing that Hall effect sensor. So it is magnetically isolated. So it's behavior like a transformer. Okay, directly we are getting some output voltage across your Hall effect voltage sensor. Okay, or Hall effect voltage transducer. Directly we are getting that signal. Okay, so that is your actual signal, and that signal is not so much so big. That is minimum nominal voltage you are getting. Okay, suppose there is range, maybe 100 volts are coming, you are getting maybe around 2 volt like that. Scaling down of voltage as well as isolating. So that is input side isolations. Then what happened? We are analyzing that voltage. So that voltage will be compared with the reference voltage. Means actual means reference voltage means set point voltage. Suppose your set point voltage is 12 volt. That should be your reference voltage output. Actual output should come that voltage. Okay. So that may be your 12 volt. Now you have to scaling down the 12 volt to 2 volt. Okay. Otherwise, how to get that voltage error? Then you are getting that error. Okay, after getting the error, what happened? It's an almost DC. Then passing through that voltage error signal to that compensator or controller circuit, and will get the control circuit. Then you are comparing with some repeating sequence. Okay, so repeating sequence is there, so you will get some PWM. Now that PWM is feeding to that gate terminals of that control switch. So there is again some isolation is required. So what we are using? Sometimes we are using opto isolators, optical isolations. Different. You can also use some isolated transformer also. Okay, but normally we are using opto-isolators. Okay, isolated transformer also you can use, no problem. So opto-isolator will be used. Then some buffer circuit we have to use. Otherwise, there is a chances for the loading effect. Okay, loading effect. Then TP5 timer is there. Then we will send that signal to the get terminal. So I think you are able to understand that the protection of your control circuit from your output terminal as well as when you are sending out that signal to the gate driver. So both of the protections are given to. So that is happened for the isolated gate driver circuit. Okay, but non-isolated, that protection is not there. Second protection is not there. So there is a chances or fast protection is also sometimes not there. But normally we are not giving the second protections. Okay. For fast protection, whatever, we can also use the voltage dividing circuit. Suppose you are designing for nominal cost circuit. So it's not possible to use 5,000 rupees for that voltage sensor. It's not possible. You are want to make a circuit that cost is maximum 500 rupees. So you cannot use that sensor. So what you can use? You can use voltage divider circuit to directly fetch that voltage. Okay, so we are talking about that isolated gate driver circuit where the second protections before giving the before sending the pulse to your get of that MOSFET or control switch, that protection is not there. That isolation is not there. That is called non-isolated. Okay, I hope you are all people have understand. So what is the motivations for the gate driver circuit and what is isolated and non-isolated? Are you getting my points? Hello.
Yes, sir.
Yes, sir. Okay, good. Okay, so now what we are doing here in this simulations, okay, we are preparing one circuit. Okay, we are preparing one circuit, and based on the circuit, what we are doing, we can see the PWM. Okay, that PWM can be fed to your control switch. Okay, based on that modifications, we are doing here some additional. We are doing here some generalized structure. Okay, and we're doing here some generalized structure, and that can be modified. Okay, that circuit can be modified based on your requirement. So what here you can see first non-isolated gate driver. So what we can see first, you can see three op amps we are using. The TL084 Texas Instrument op amp is there. Okay, so one op amp having one TL084 chip or IC having 4 op amps. Okay, so here we are using 3 op amps. Okay, one single TL084 having 4 op amps. We are using 3 among of them. Okay, one is not using. Basically, it's not required. That's why we are not using. Okay, that's why you can see it is starting 2, 3, then 5, 6. Actually, 1 is your output for the first op amp. 2 is non-inverting terminal, 3 is your non-inverting terminal. So my suggestion is that please download the data sheet of TL084. Okay, and see which one is their VCC. Okay, one VCC terminal is there. Okay, so you can see the VCC terminals are plus VCC means plus biasing voltage terminal is terminal 4 and negative VCC. Okay, that voltage is 11. That terminal is 11. Okay, one ground terminal also be there. Okay, plus VCC minus VCC. So total 4 op amps are there. 3 into 4. Okay, 12. Are you getting my point? Another one is plus VCC, another is minus VCC. Total 14. Okay, so 14 legs are there. Okay, so 14 legs are there. So in this TL084, you please download the data sheet and see what are the terminals. Okay, like when you are using some microcontrollers. So if you have the name of the microcontroller, so what we are doing, the pin diagram of the microcontroller. So pin diagram of TL084 also required for this one. So that is not given in this manual. It is not here, but you should download it and you need to cross check it. Okay, what is that value? Okay, I hope you are getting my point. So here first op amp is there, okay, for generating the triangular waveform. Okay, how is it operating? Okay, so here you can see back to back zener is there, 5 volt, 5 volt. So plus minus 10 volt we are getting. Okay, so then what happened? You see capacitor. Okay, it's a small ceramic capacitor. Okay, small ceramic capacitor. Okay, so that charging discharging based on that voltage we are getting, what happened, we are getting a triangular voltage. But the range, the height of the triangular voltage is, you have to cross check it for individual points. Okay, individual points you have to cross check it. Okay, how the waveforms are coming. So from the circuit the triangular waveform should be generated. It should be generated. Okay, and the frequency of the triangular waveform can be varied by this R4 resistance. Okay, so you can say like that, suppose 50% if you want that R, so how much frequency is coming? Okay, it's a pot type of thing, pot. Okay, two fixed terminal, one variable terminal. So that is one pot R4, that is 5K. Okay, another pot is there, that is 5K. Okay, that key A, so that is another pot is there. Okay, so what happen if you vary that value? So charging discharging time also will vary. Okay, RC circuit, it's an RC. This is R, this is C. Okay, so what happen? The frequency of the triangular waveform will be varied. Okay, so from where we are getting, from where we are generating the repeating sequence. So from this circuit we are generating the repeating sequence. Then what happened? Here you can see inverting amplifier. Okay, so it's not that non-inverting, it's an inverting amplifier. Here you can see. Okay, what is the gain of that inverting amplifier? Okay, so 1 plus RF by what? Feedback by input, RI. Okay, that multiplications are there. Okay, so whatever triangular waveforms you are getting, so their height will be increased over there. Okay, so if the height of that waveforms has been increased, so what you are getting, so you will get that triangular waveform with having more amplitude of this first oscillator, so first defined op amp. Okay, so first the purpose of the first op amp is generating the triangular waveform. The purpose of the second op amp, you can see the terminals is connecting that 5, 6 and 7. Okay, VCC are common for all the cases, VCC VE. So minus and plus, so all those cases minus minus connected over there, minus minus connected over there, plus plus. So you cross check it. Okay, whatever you are doing, the terminal you should cross check it. Otherwise, if that VCC terminal you are connecting wrong side, that's why I told you to download the datasheet. Plus VCC terminal should be connected with plus voltage, plus 15 voltage, and minus VCC terminal should be connected with that minus 15 voltage. If you are not connecting, so the problem will be occurred. Okay. So then that value will be amplified over there. After amplifications, what happened? You are using the pot. Okay. So what is the purpose of this circuit pot? So I'm talking about that after control voltage. First, we are getting that set point value of voltage. Then we are comparing the set voltage with some actual voltage. We'll get some error signal. Okay. After error signal, what we are doing, we are sending up that error voltage error to the compensator. I will get almost fixed voltage, DC voltage. Slowly varying DC voltage, that can be as the voltage mode control is fixed. Okay, so that voltage will be generated by this pot circuit. By this, here you can see by this pot circuit. Okay, that voltage can be generated. Okay, here. Okay, so that voltage can be generated from here. Okay, so now we are comparing the triangular one. So we have to use some scope. Okay, so why the scope is required? That we need to see both the terminal. For individual terminal, we have to see what is the pattern of the waveform, how is it coming. Okay, so if that voltage, okay, DC voltage is beyond of your triangular waveform, so there will be no comparison. Okay, there will be no comparison. So PWM will not be generated. So one oscilloscope should be connected over there to see, okay, how both the voltages coming. Both are cutting each other. Both that DC voltage should be come inside of that repeating sequence. If it is not there, then you should vary that pot. Okay, and finally we'll get that PWM. So plus VCC to minus VCC. But minus voltage is not required. That's why one diode is given. So minus portion will be omitted. So there will be no minus portion. Suppose for bridge converter, if you want to do, then what happen? You should use that negative terminal, that negative pulse for you can invert that negative pulse. Okay. Suppose one signal will be there. Okay. Through that diode, another signal will be there that can be invert of this signal, then passing through the diode. So you will get another pulse. Okay, you will get another pulse for the bridge type of circuit. Both the pulse are required full bridge circuit. Then you are giving it the stable multiplier, that is 555 timers. Okay, and you will get that output. So what kind of output? Pulse output will be there. But what happened in stable multivibrator? Okay, so when Smith trigger or 555 timer, so whatever pulse you are getting the inverting pulse. Okay, you are getting that inverting pulse. Okay, so so you have to sequence, you have to maintain the sequence such a manner so that inverting pulse should be eligible to feed the diode. What do you mean by should be eligible? Suppose you are considering, okay, so that control signal, error signal is more. Error signal is more means your actual voltage value and reference voltage value, there is differentiate more. The gap, that means residue of the difference or difference of that actual voltage and reference voltage is more. Then what happen? Error will be more. So how do you minimize that error? So you have to make more on time for the switch to compensate that error. Okay, so what will be the logic? The on time durations or pulse duration will be more. Okay, so that's why what you need to do, that's why what you need to do, you have to increase the pulse value. Okay, so you have to increase that. Then you can understand if you want to increase the that voltage is more, okay, error is more, and the pulse width also should be more. On time pulse width, not off time. Only that conditions the error can be minimized. Okay, you have to cross check it both the end. So logically, then you can understand your gate driver is okay and it can be working for that conditions. You are getting my point? Next, what happened? Sorry. So here the tables are given. So what are the basic parameters? You can observe the output of individual op-amps. Okay, so terminals of first, second op-amp, triangular, how it is coming, how the pulse and triangulars are coming. Okay, so both the case you can easily understand from these diagrams. Then 50% for R4. Okay, so both the conditions are there. Okay, frequency is if you decrease that R4 or increase the R4 is the changes of the frequency. You can see the pulse width has been varied. Okay. Now we are talking about isolated type gate driver. Okay, so what we are doing, what kind of isolation we are doing? We are using opto isolated MCT2E. MCT2E we are using over there after that gate pulse. So we are isolating that output of that 555 timer and that generating pulse from that op amp. So both the circuit will be isolated. Okay, by using MCT2E. Okay, so the configurations are given over here. Okay, from that configuration, we directly get that value. So for MCT2E, another important point, important instruction is that if we are using MCT2E, one inversion will be there. Okay, so that's why whatever conditions are there, getting over here. So if we are using MCT2E, so inverting response we are getting. For 555, again inversion will be there. Finally, we'll get the genuine one, what we are required. Okay, so what pulse here there, that should be in phase with that output one. Okay, so that you should keep in your mind. So rest of the portion is same. So and only opto isolator is there for getting. So you can also use that multiple of opto isolator for multiple pulses also. Okay. So as well as some transient configuration, some movies are given for isolating gate driver circuit, how they are varying. Okay, so I hope you are able to understand what is that one. All of you getting my point? Any doubt from your end? Is there any doubt?
No, sir. No, sir.
Okay. So I hope all of you are able to understand. So any problem is there, so please let me know. Okay, so I hope you are able to understand. So any problem if you have encountered, please let me know. So I can, that portion I can rediscuss. Okay. I'll share this document with you. So one by one, you can share me your simulation. Okay, who want to share me the simulation of your previous work? Want to share me?
Sir, I'm saying.
Okay, please share it.
This is the semiconductor with R load.
Just what happened? Can you please just let me?
Semiconductor.
Bishwajit,
Yes, sir.
Bishwajit,
Yes, sir.
make it zoom. Actually, I'm not able to see. Just for a moment, maybe my system. Okay, now okay, fine. Please let me know. Tell me.
This
60
is.
volt.
Yes, sir.
Okay, you are
Alpha equal to
considering
60.
60 volt. So this is for semi converter.
Yes, sir.
Okay.
Uh, these are the input voltages, three-phase input voltage, and the gate pulses are there. And this is the output, and this is current.
So gate pulse is 60 volt. Okay. Sorry, 60 degree. So can you
Yes,
please
sir.
make it more?
Yes. 90 degree.
Acha, now it is 90 degree.
Yes,
Now
sir.
show me the response. How is it? Okay. Output voltage. This is your output voltage.
Uh, yes, sir. The red color is the output voltage, and the blue one is the current.
Can you please discuss it? Why these kinds of natures are coming? For 60 volt, the nature was
Uh,
different. Am I right?
yes, sir.
Why these kinds of natures are coming? Can you please tell me?
Sir, sir, for 60 volts, the voltage is decreasing to like here, and after that it is again increasing. But when it is 90 volt, the next thyristor is triggered later, so the voltage decreases till that point. But if it is less than 60, is it is less than equal to 60, the next thyristor will be turned on before decreasing that up to that value. So that's why this is coming like this.
Okay, that may be the reason.
Yes, sir.
Okay. Okay. For other load, you please show me.
Yes, sir. This is for RL load, uh, and alpha is 60 degree. Uh, here for the current, we can see that if for the only R load, the current was directly following the voltage. So, but here we can see that the shape is little bit different because of the inductor.
Okay.
Okay. This is RLE load.
With 60 degree.
Yes, sir. RLE load 60 degree. The E value is 50 volt. Uh, this is for alpha equals to 120 degree. Uh, Alpha equals to 120, when alpha equals to 120 degree, the voltage is decrease. The For a certain period of time, the one thyristor is conducting. So and after that, it is decreasing till the next thyristor is conducting. And so during that zero current period, so output voltage becomes E. E, that is 50 volt
Hmm.
in this period. And again, when the thyristor is conducting, the voltage increases and
Okay.
becomes this one.
Acha, if you increase, acha, that is for 60 degree, 120 degree.
120 degree. Yes, sir.
So make it 150. I think what happened. Let me check.
Similar.
Similar though.
Yes, sir.
Hmm. Okay, good. So if we increase that E value,
Yes.
now make it E 150. Let me check. Make it 150. Hmm. Are you able to understand now what happened?
Yes, sir. Yes, sir.
Okay, good. Acha, Vishwajit,
Yes.
do you prepare that last class I told you for all the converter one table I am asking for it regarding the efficiency and output voltage means do you prepare that table? One sheet I told all of you to prepare.
No, sir, I haven't done.
Okay, so you please show me it in my next class. Okay.
Yes, sir.
Actually, that's really important. Okay, that's really important to know actually. Okay, to compare all those control converter. Okay, so why it is important? Mane, which one should be suitable for semi-converter, converter, single phase, three phase, and the point of view, the efficiency. Okay, and utilization factor. You getting my
Yes, sir.
point?
Yes, sir.
Okay, good. Next, who want to show the simulation? I have posted that manual in your chat box. Please check it. that file, PDF file? Hello? Do you
Yes,
receive
sir.
that file?
Yes.
Next, you want to show me the simulation? No one is interested. Hmm? Roll number 284. Roll number 284. Absent, okay. Roll number 268.
Yes, sir.
Show me your simulation.
Sir, I have messaged the CR regarding my issue, laptop issue. I don't have a source to show my simulation file or screen, share the screen, sir.
You are also
I have,
not showing me the simulation. Good, very good.
yes,
No
no,
problem.
sir, yes. Sir, yes, I have
Number,
proofs. Too, sir.
roll number 270.
Yes, sir.
Show me your simulation.
Yes, sir. So can you see? Hello? Sir, I'm
Only
sharing
black.
screen.
Yeah. I'm not able to see the file. Only black screen I can see.
Sharing.
And now
Just a
it is
second.
visible. Now it is visible.
Okay, okay. So this is for 90 degrees.
For RLE
Only
load.
current.
What about other load?
Uh, for RL, actually, I have made only one design. I just delete it. Oh, shit. This is for RL.
Simulate it, simulate it.
Yes, sir. This is the result. For RL load, 60 degrees.
This is your result for 60 degree.
Yes.
Is it correct? Do you know? Is it correct or is the result is okay? Is it correct? Aditya? Aditya?
Yes, sir.
Please explain your
Yes, sir.
results. Please explain your results. Why this is come this type of waveform? Explain it.
Sir, I think it's correct.
You think this is correct? Okay, then tell me why. Justify your opinion. My question is that please justify your opinion. If it is correct, please justify your opinion. What happened? Please justify your result.
Sir, actually, it's not. I just
So you are not giving the proper justifications. Okay, good, very good, no problem. Okay, next, who want to show me the simulation? Anybody else who want to show me the simulation? Kumal Krishna Behera?
Hello? Yes, sir.
Do you want to show me your simulation?
Yes, sir.
So show me your
Yes.
simulation.
So is my screen visible?
Till now, it is not visible.
Sir, 1 minute. Sir, is it visible now?
It is visible now.
Yes, sir. This is for R load and sir, so like it's little slow. Sir, is it visible?
Yes, it is visible. Okay, please explain your results.
So like the first one is like the input voltage, then output voltage. After that, so like the first is input voltage, then this one is the output voltage, the third one.
Hmm. No, my question is that, can you please explain why this kind of patterns are coming? Explain me the patterns of your results.
Patterns. So like the for the delay, like we can see that uh
Delay.
it's not delay, so like the firing angle, uh like it is 30 degree. For 30 degree, I've done this. So like there will be three phase, like in three phases there will be pulses.
Okay, that's okay. But my question is that, can you please zoom your one cycle?
So
Can you please zoom one cycle?
yes, sir, okay, sir, I'm trying to. Yes, sir, I'm trying to. Sir, is it visible?
I want to ask you for zoom that output voltage for one cycle.
Yes, sir, actually my laptop got hanged one.
So why you are not using multisim?
Sir, like my laptop doesn't has that configuration for multi-sim, so whenever I download it, gives error. Sir, 1 minute, sir. Sir, my laptop got hanged. Sir, output voltage, sir.
Yes, output voltage. I think this is R load, am I right?
Yes, sir. R load.
Okay, how would I
Like
understand this
here
is R
only
load?
it's much like I'm not able to zoom it more. So like I'm doing this X. Sir, like it's not. So like hello. Sir,
Huh,
for sir, like
tell me.
for like I am not able to zoom anymore.
You are not
Sir,
able to zoom. Acha,
sir, I am
please
sir
explain
like
your results.
access.
Please explain your results.
Sir,
Please explain your results. Give the proper justifications of your results.
so for resistive load, um, so like the output, like the waveform will be same, like the output and the input. Yes, sir, it will be like
Output
same.
and input like the same means what kind of answer you are giving to me?
So like waveform will be same because there will not be any phase difference because the load is only R load.
Okay, I'm asking about the justifications of your average output voltage. Why that patterns are coming like that? That is my question. That
Oh,
waveforms are, that's why I'm telling now this is R load. Voltage and current are in phase.
yes,
Okay.
sir.
That's why it is unload. There is no doubt on it. My point is that can you please explain how that waveforms means output voltage waveforms, how is it coming? That's why I'm telling you, make it a zoom for one cycle and give me the crystal clear idea about your response, about your results. That is my point.
Okay, sir. So like here we can see that the like I have done firing angle is 30 degrees. So like the firing angle is less than 60 degree.
Hmm.
So we are getting 6 pulses. So like that is the pattern. Like per cycle we will get 6 pulses.
Okay, that's fine. After giving the firing pulse, it is goes up. Okay, then why suddenly goes down again goes up? Why that kind of natures are coming? That's my point. So both the converters are
So
not
like
working
holding current.
simultaneously.
So like first there was conduction and then due
Then
to
what
holding
hap-
current.
Then second, why the second one is not working? Mane, what is the problem with that?
Uh,
Okay, so you are not giving me the proper justification. My suggestion is that please go through that one. Go through that waveforms. What kind of waveform you are getting? If you don't have that much amount confident about the result, please go through it at the time of exam. Okay, so I'll ask each and every points of that as a justifications. And you have to write it in your copy. It's not like that we are not writing anything and just doing the simulation. No, doing the simulation is important part, but how would I cross check it? That simulations you are properly understand or not. So that's why justifications portion is very important. Okay, please try to understand and explain.
okay, sir.
Okay, okay, please complete it. Okay,
Yes, sir.
it's not a complicated one, very simple thing. Okay, so why justification is important? Na? So there otherwise no meaning to doing the simulations.
Yes, sir. Okay, sir.
Okay,
I'll do it.
okay, okay. And all other students, those who have not able to complete all those portions, please complete it. Okay, next class I want to see that the simulation of gate driver circuit and the table. Okay, where the table should comply or the table should contains all kinds of converters. Okay, their efficiency, utilization factor, input voltage, output voltage, whatever values are coming. Okay, so from that we can understand which converter is efficient more. I mean, which converter we need to use for some of the applications. Okay, that is very important and required to us. Okay, please show me in my next class. Okay. So now we are conducting that MCQ test. Hey, Bikash and Suchi.